Okay, folks, so today we're going to start in looking at the chi-square distribution. So I want to just show you in our class pages where you ought to look for the notes and examples that I'm going to work through today. I will make sure I publish this Chapter 11, Inference for Categorical Variables. I'll go ahead and publish it now. So you should be able to see this button for Chapter 11 if you scroll down. If you want a paper copy of what we're working through, I'll be doing the alternate example student copies. Those are usually what I work through in class with you. And then if you want to get some extra practice, these are the practice worksheets that we do in class that I usually give you the answers as well. So the answers will be there so you can sort of gauge how well you understand the material after we go through the examples. You can try some of the practice problems and see if you got the hang of what we're working on. So all that will be available there. Okay, so I want to just talk for a second about the chi-square distribution. So if you look at your formula sheet, you'll notice this is where we've been, right? You just took the Chapter 10 test. Most of you did really well on that too, by the way. So good job with the Chapter 10 stuff. But that was two different populations, right? Difference in means or difference in proportions. And then all of a sudden you see snuck in down here at the bottom is this chi-squared test statistic. I think it's the easiest test statistic that we work with. You can almost see the simplicity of it from the formula. The capital sigma means that we're going to sum up. So what happens with chi-squared is a lot like what we've been doing with inference in general. There's something we expect to be true, right? Like a null hypothesis. We expect, if we roll a die many times, we expect the numbers to be equally likely, right? That might be our expectation. But then something maybe different happens that we observe. So like if I rolled a die 120 times, I'd expect on average to get about 20 of each number, right? 21s, 22s. Now, we all know I won't get exactly 21s and exactly 22s. That would be really unlikely to get 20 of each. But I should be pretty close to 20 of each. I shouldn't be too terribly far off. Like if I got no ones, right? So my observed value would be 0 and my expected to be 20. There's a big difference between those. So the way chi-squared works is if we get a big sum of differences, then we're believing that something is different from what is expected. And, you know, what is expected will be our null hypothesis. Same kind of concept that we had with our other hypothesis test. Now, the other difference in chi-squared is when you look at the distribution right away, you're going to notice it's not normal. It's skewed right. So everything is always a right-tailed test. We don't have to worry about left-tailed test or two-tailed. In fact, we write the null and alternate hypothesis a little less formally. We don't need the equation so much anymore for the chi-squared test. But that's the other thing I think that makes chi-squared easier to work with is everything, if we get a really big number, then we know that it's significant. So what would we consider a really big number? It depends on our degrees of freedom. It depends what we're measuring. So degrees of freedom, and depending on which chi-squared test we do the degrees of freedom a little bit differently. The one test we'll look at today, the goodness of fit test, which is really pretty simple. It's just number of categories minus 1. So suppose I was checking to see if a die was a fair die. Well, there's 6 sides to a die, so that would be 5 degrees freedom, 6 minus 1. Okay, and you can see the bigger the chi-square statistics, right, the more significant, right? The p-values are getting lower and lower and lower, right? Here's a really small p-value if my chi-squared with like 5 degrees freedom is 22.11. So we're going to be able to rely on the calculator a lot as well today, but let's jump into it. A little bit of chi-squared practice. So I showed you in your class page where you can find this document if you want to have a paper copy of it to work along. Okay. But here I have a ceramic die that Jenny is testing out, and she wants to see, eventually we'll test this die against 5 degrees freedom and see if there's significant differences. So she rolls the die 60 times. And that's another thing we're going to talk about. There's no expectation for normality. So when you're checking your conditions for inference, of course, you'll want a simple random sample. But you don't check normality for chi-squared. If you say something about normality for chi-squared, you kind of lose points right away for that because you just saw it's a skewed right distribution. It's not a normal distribution. So that's, in my opinion, that's kind of good. But we do have a expectation on our expected counts. We need these expected counts. Right, if we really want to make a valid inference, we need them all to be at least 5. All right, so that's our rule of thumb. We need our expected counts to be 5. So we'll be fine here. We're testing this die. So if we want to do a legitimate test of a die, we need to roll it at least 30 times. Probably a good idea to go ahead and roll it 60. All right. So I want to calculate the chi-squared test statistic. And it's a hard K sound. The chi-squared statistic is, it's not chi-squared, it's chi, right? So what I would do to get my chi-squared statistic here, and I'm going to go to the calculator next to actually do this, but I would take each observed and expected. So I would take 13 minus 10. I square that. So it's observed minus expected, and then we divide by the expected. And then we add that to the next one. 11 minus 10. We square that. We divide by 10. And so on. And I would have 6 of those. So right now what I'd like to do is go to the calculator and see how it would work on there. Okay, so first thing I do when I have lists, and we've been saying this for a while now, you're going to go, once you have lists, which I have in this situation, it's going to go to stat and edit, or go to your spreadsheet on the Nspire. So maybe pause the video for a second and enter those numbers, right? Notice I put my observed in my list 1 and my expected counts in my list 2. So I have to pay attention to those for what's going to happen next. I could build up this third list here. I could do L3 equals parentheses L1 minus L2 squared. We could do that, sum all, and then sum all those up and divide. But it's just going to be much easier if we go right to our stat test menu from here. I'll show you what I mean. So we go to stat and test, and your calculator, unless it's really old, should have both chi-squared tests on here. So we are going to be working with this chi-squared test. This is the goodness of fit, right? This is answering a question like where I have a list of numbers. Maybe it's, colors of Skittles or colors of M&Ms, and they're supposed to follow a certain proportional distribution. Maybe it's the number of times numbers came up when I'm rolling a die. But that's what the goodness of fit test feels like. The other chi-squared, there's 2 different names depending on how you gather your data, but they're both chi-squared tests. We'll get into those in the second half of this chapter, but there's some just technical ways that they both are going to feel and look the same. You set them up exactly the same. There's just a small difference in some of the wording with those other 2 chi-squared tests. So we're looking at chi-squared goodness of fit right now. So when I go to my goodness of fit test, all I have to do is tell the calculator where my observed list is and my expected. Now I do have to know my rule for degrees of freedom. I don't think your calculator does this for you. So make sure your degrees of freedom is correct. If it's not, you'll get the wrong p-value. Okay, they'll still do the chi-square test statistic correctly, but the p-value will be wrong. So now when I calculate, you'll notice the chi-squared test did everything for me. P-value is 0.63. And then these numbers here, what are they? Well, this 0.9 is what you get. Oops. That 0.9 is what you get when you take 13 minus 10 and square it and then divide by 10, right? We get 9 divided by 10 is 9/10. So it gives you each of those 6 little components. So what's helpful to that is if I run a chi-square test, then my next, if this p-value was low, if we decided this die is not fair, the next obvious question would be, well, how is it not fair, right? What number is, or numbers are occurring disproportionately than how they ought to? And that's where I could look at these contributing factors and I'd look for which one of these is the biggest value contributing to that chi-squared value. Okay. All right. So let's look at the next question that relates to our chi-squared distribution. So that was calculate the chi-squared statistic. So the chi-squared statistic there was 3.4. Okay. So if we're keeping score there, so I write chi-squared equals 3.4. Okay. And we can just use the calculator. You saw where that would come from in the calculator, but we can lean on the calculator to do that work for it. Okay, so I want to move on to the next example. And they just come right alongside us with using the appropriate degrees of freedom, calculate the p-value. So we would have 5 degrees of freedom. If we go back and look at our formula sheet, we could estimate what our p-value would be. Okay, if I have 5 degrees of freedom, I can see that my chi-squared statistic was 3.4. My chart only starts at 6.63. So if chi-squared was 6.63, we'd already have a p-value of 0.25. So if we're only at 3, right, so 6.63 is here, and the p-value is 0.25, 3 would be back here somewhere. So we would know that our p-value, all we could say is the p-value is greater than 0.25. But we can do better than that. We have our calculator that tells us that p-value is 0.64, okay? So I get that right off of my calculator. The p-value would be 0.64. Okay, so if she was testing to see if the die was fair, right, the null hypothesis would be something like this die follows the distribution of a normal fair die. And your conclusion would be you'd fail to reject that null hypothesis. So you don't have any significant evidence that her die doesn't behave like any other fair six-sided die. Okay, so when we read this question here, this should look familiar. Do these data provide convincing evidence? So if you have your hypothesis test template handy, that is where we're going to be going. Okay, this is for sure a hypothesis test start to finish. Anytime they say, do these data provide convincing evidence? So I'm going to show you what the chi-squared test is going to look like, and I think it's the easiest test that we do, especially the goodness of fit one. So let's look at the setup here. What do we have? The U.S. Census says that the residents, or the ages of residents, follow this particular distribution. 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, and 22.8% are 60 and older. So we found a group of people that were chosen at random using dialing landlines, right? So this is the distribution of people that answered landline phones out of 1,048. So we want to see, is this really far different from these percentages up here? In other words, is 141 out of 1048 very different from 19.1%, or is 186 divided by 1048 very different from 21.5%? Significantly different, or somewhere in there, is this distribution of people who would answer their landlines different from the distribution of all people that we would find in the U.S. according to the census? So the expected counts are really pretty easy, right? I'm sorry, our observed counts are really very easy. I just copy them off of what they gave me. So next door in my second list, I need my expected counts. Okay, so let's think for a second. How are we going to get our expected counts? How many people? We got 141, that's what we observed. But how many do we expect to be in their 20s? Well, it says up here 19.1%. So I'm going to take 19.1% of the total. So it would be 1048 times 0.191. So that's how many I expect. So there's a difference there, but again, we have to examine whether or not these differences are significant. That's what we're going for. The proportion that are in their 30s should be 21.5% of that 1048. So all right, 0.215 times 1048. Okay, and I'll get my expected counts to match up with those. Okay, so let's see what we have. Check your expected counts, make sure they're the same as mine. Two lists should look like this. We have our observed and our expected. I just took the percentages they gave me and multiplied them by the sample size, and you can see it's okay to have decimals for your expected counts. Okay, so chi-squared is going to make this real easy for us. We go to chi-squared test. Just scroll up or find that goodness of fit test. Let the calculator know where your two lists are, and I think our degrees freedom needs some adjusting here, right? If I'm not mistaken, there were only 5 categories. 1, 2, 3, 4, 5, yep. So that means we now have 4 degrees of freedom. So we have to watch that. It's not going to, when we do our other chi-squared tests, it'll do the degrees of freedom for us. This does not. And we just, I really don't know why. I think the calculator ought to be able to look at your lists and see how many are in there, but there's different uses for chi-squared, so you have to set the degrees of freedom yourself. Okay, so there's my test statistic, and don't get fooled. This is a really small p-value, right? Look, it's times 10 to the negative, or yeah, times 10 to the negative 10th. So it would be a decimal, 9 zeros, and then these are your contributing factors. So it's really, really obvious. This is going to be strong evidence that the proportion of people that answer landline phones is different from the proportion of all U.S. adults, and we can probably infer the reason for that. The people probably on the younger scale of that, the people in their 20s and 30s. I know for myself, I haven't had a landline in many years, so and probably the younger you are, the less likely you're going to be to have a landline. So my parameter of interest, this is going to look a little bit different, right? In fact, you probably don't even really have to talk about a parameter of interest with the chi-square distribution, but this is the distribution of people of ages. So my null hypothesis, I will still set up a null hypothesis, but my null hypothesis would be that the distribution people who answer landlines, say age distribution, and then the alternate would be that the two distributions are not the same. So I think that's easier than our usual null alternate hypothesis. We still always want to get an SRS, and I do think that they said that this was, randomly, this is members of sample were chosen by randomly dialing. So we have that for us. Oops. So we are randomly dialing here. We don't check normality, okay? Our expected counts then 5. That's all we need, okay? So we did a chi-square test. Goodness of fit test. If I could do my chi-squared symbol here, I would, but I'm just going to write chi-squared equals, what was that number? 48.17. P-value is very, very small. So when it's that small, I'll just write something like it's less than 0.001. Okay, you can write 8.9 times 10 to the negative. Okay, so we would reject H naught. Something along those lines. So let me just double back here and see if we have any other examples. I think that's the last of our examples today. This is just your chi-squared test statistics. So this shows you your contributing factors, right? Where were the biggest discrepancies in the 20-year-olds and the 50-year-olds, right? These folks here probably more likely to have landlines than what we experience, and down here these folks less likely. So that's where the two largest discrepancies were. We can look at those, but your calculator lists them as well. If you see them right here, see the 17.48 and so on. That's where those numbers are coming from. Okay, there's those contributing factors. Okay, and they're rounding a little bit differently. Our calculator is probably a more precise estimate.